Today we will discuss the last of the 4 tools that are part of the data mining coverage. We're done discussing chapters 10, 12, and 13, and now we move on to chapter 14, which is called Simple Linear Regression. And as we can see in the matrix again, the simple linear regression is now used to find relationships between 2 quantitative variables. So chapter 14 is called again the simple linear regression chapter. Now compared to the 3 other tests that we have discussed so far, simple linear regression actually has 3 uses. It has a lot of uses because we are dealing with quantitative variables. Now the first use of the simple linear regression is that this can be used to build a regression model. Now a regression model is basically an equation that shows the relationship between x and y, and usually it's in the form of the slope-intercept form of equation. So we have here y, this is the dependent variable, equal to beta sub 1 x plus beta sub 0 or beta naught plus epsilon. Okay, so beta sub 1, this refers to the slope. So this is the change in the dependent variable for every unit change in the value of the independent variable x. While beta naught, this is the y-intercept. So this is the average value for y if the value for x is 0. And then epsilon, we have here another parameter called epsilon, and this is the sum of all the other factors that can affect y. Because for simple linear regression, we are limiting the discussion to just 2 variables, x and y. And we know that in reality, there might be some other variables that can affect the value of y, and all of those are included in this value epsilon. Okay, so this equation refers to the regression model for the entire population, for all possible values of x and y. And in most cases, this information is not available, so we can only come up with an estimated regression model, and that is in this form. So that's y hat equal to b sub 1x plus b sub 0 or b naught, and y hat here is the sample, or this is the statistic for the dependent variable. So this is the predicted value for y. B sub 1, this is the sample slope. X, this is the independent variable, and then b sub 0 or b naught, this is the sample y-intercept. And again, all these values will be coming from your sample of information. And since data just comes from a sample, the slope and the intercept that we will get from our computations might not necessarily be correct or accurate. And for us to know if they're actually correct, or if the values are correct or are good estimates of the slope and the intercept, we have to perform 2 hypothesis tests. The first one is to try to test if the slope is equal to 0 if it's not equal to 0. Because again, the sample computations will provide a value to this, but we don't really know if this is really the value for the entire population. And for us to test if this is significant, so we have to test if it's equal to 0 or not equal to 0. So if we can have enough evidence to show that the slope is not equal to 0, then most likely the value that we got here is significant. At the same time, we also have to test the significance of the intercept. So same process. You have to test if it's equal to 0 or if it's not equal to 0. And if you can say, or if you have enough evidence to say that the y-intercept is not equal to 0, then it means that the intercept that we got earlier from our sample is also significant. So if both the slope and intercept are significant, then it means that the estimated regression model that we were able to get from our sample is also significant, which means that we can use this to predict the value for y. So if you have a certain value for x, and if you plug in that value of x to this formula, then this y hat is the predicted value. So this is the predicted value for the dependent variable if the value for the independent variable is equal to x. So that's the first use. Now the other use of the simple linear regression model is that we can test the correlation between 2 quantitative variables. So now we move on to how we can identify if a relationship exists between the two quantitative variables. And for us to do that, it's very similar to what we did earlier. Here, to test the correlation, we just have to test if the slope is equal to 0 or if it's not equal to 0. Now, why is this enough? Why will this be enough for us to know if there's a relationship between two quantitative variables? Because here, we are trying to test if the slope is equal to or if it's not equal to 0. And if you try to visualize the graph of an equation, the graph of a line where the slope is equal to 0, it will be a horizontal line, which means that for every increase in x, there is no change in y. So if we can say that the slope is not equal to 0, so regardless of the sign, if it's negative or if it's positive, then it means that the slope, that the value of, as the value of x changes, there's a corresponding change in y. So even if it's negative, it means that as x increases, y decreases. Or if it's positive, as x increases, y also increases. As long as you can say that the slope is not equal to 0, then we can say that there is a relationship between the two quantitative variables. So that's the second use. Now, the third use of the simple linear regression is that we can actually measure the strength of the relationship. So this can only be done for simple linear regression as compared to the first three. Now, to measure the strength of the correlation, we have two computations. The first one is the coefficient of determination r squared. So this is commonly reflected every time you perform simple linear regression. And then another one is called the simple or the Pearson correlation coefficient r. Now, the coefficient of determination r squared refers to the percent or the percentage or the proportion of the variation that can be explained by the model. So if the r squared is equal to 90%, it means that 90% of all the variation for y can actually be explained by the formula or by the regression model. So it means that the closer r squared is to 100%, then the stronger the relationship that exists between the two. Now, r is simply the square root of r squared, and for this case, it's also interpreted similarly. So if the value for r is close to 1, then we have a strong relationship. Now, since we are getting by getting the square root of r squared, then r can be negative or positive, and that depends on the sign of the slope. So if your slope that you determined earlier is negative, then your r will also be negative. But if your slope earlier is positive, then your r will be positive. So to simplify how to interpret r, the closer r is to -1, then we have the stronger the negative correlation, but the closer r is to +1, then the stronger the positive correlation. So that's the third use. We can actually measure the strength of the correlation using the simple linear regression. Now, we don't really have a standard way of interpreting if the correlation is weak, if it's strong, or if it's very strong. Usually, we just look at the value of r squared and then compare that to another r squared for us to interpret the strength of the relationship. But we don't really have an accepted way, accepted range, similar to what we have for the weight of evidence. So we don't really have something similar for measuring the strength. Now, to test if the simple linear regression will be valid, a simple way to do that is to just ensure that your sampling distribution is normal. So meaning you have at least 30 pairs for the values of x and y. And similar to ANOVA, there are actually a lot of assumptions for simple linear regression, and we will discuss how to test the assumptions to see if the assumptions are satisfied later on for us to be able to make the necessary interpretations. And to prepare the data, it's relatively simple. You just have to copy one dependent variable in one column and then another independent variable in another column. So for this case, you don't really need to do a lot of sorting. You just have to copy x and y to another worksheet. Now, just like other statistical tests, the simple linear regression model has its assumptions, wherein the validity of the results of the regression analysis is based on the satisfaction of the assumptions of the use of the model, such that if the assumptions of the model are not present or are violated, then it means that the simple linear regression analysis or regression analysis in general might not produce accurate results, and the interpretations might not be valid for all the values of x and y, or all the values of the dependent and the independent variables. So for simple linear regression, these are the assumptions. First is an assumption for the mean of the residuals, which is 0. Next, the constant variance assumption. Third, we have the normality assumption. And finally, we have the independence assumption. So here is an illustration of the assumptions. Again, the blue line here represents the regression model, and these are the values that can be constructed using the formulas that were discussed earlier. Now, here, at this point, we have the mean yearly revenue when x is equal to 32.3. So for a particular value of x, which is 32.3, the point here on the line indicates the average. So it's possible that the actual value for y is not equal to the average, because again, there are multiple values for y. There can be different values of y, and sometimes it's lower, sometimes it's bigger than the average, but the assumption is that it follows a normal distribution. So the residuals follow a normal distribution, and the mean of the residual is at the point along the regression line. So that's also something that is shown here. So for this particular value of x, which is 61.7, the average value for y is equal to this point. And again, the possible values for y when x is equal to 61.7 follows a normal distribution with mean at this point, and then the values can be lower or higher than that point. Now, again, the model assumptions are determined or are verified by looking at the residuals. So the residuals in the regression analysis are the main basis for validating the assumptions of the regression model. And as mentioned earlier, residuals, or denoted by small letter e, are defined as the difference between the observed value of y, so the actual value of y that you obtained from your sample, and the predicted value of y, which is denoted by y hat, using the regression model. So note that e is the point estimate of the Greek letter epsilon. So epsilon refers to the population parameter, so e is only the point estimate that we obtained from the sample. So if the regression assumptions are valid, then the population of potential error terms will be normally distributed with mean 0 and variance of sigma squared. And different error terms will be statistically independent, so that's what we mean by the independence assumption mentioned earlier. Now, in order to check if the assumptions are satisfied or not, there are multiple graphs and multiple tables that we can look at. So again, residuals should behave as if they are randomly independently selected from normal populations with mean 0 and variance sigma squared. And we are not really looking for minor deviations from the assumptions. So we can only say that the assumptions are violated if there are pronounced departures from the assumptions. So if the assumption is clearly violated, then as shown in the graphs in the tables later, then that's the only time when we can say that the assumptions are violated. But if the assumptions are approximately satisfied, so it's not pronouncedly different from the assumed assumptions, then the assumptions can be considered to be satisfied and we can proceed with the regression analysis. So in most actual data, assumptions will not hold exactly. So as long as the departures are mild, it will not affect our ability to make inferences for the entire population. So as long as the residuals approximately fit the model assumptions, and that will be good enough for us to make an interpretation. So here are some specific ways for us to verify those assumptions. For the constant variance assumption, in order to check the validity, we can examine multiple residual plots. So these residual plots are basically scatter plots with different values on the x-axis and the residuals on the y-axis. So one residual plot that we can look at is the plot of the residuals against the independent variable. So you have the independent variable on the x-axis and the residuals on the y-axis. We can also look at the residual plot against the predicted y value. So on the x-axis, you have the predicted values for y, and on the y-axis, you have the residuals. And if your data is time series data, the time can also be placed in the x-axis, and on the y-axis, you will have the residuals. So what we have to look for in the residual plots is the overall pattern of the plot. So if a pattern fans out, it means that the variance is increasing. If the pattern funnels in, then it says that the variance is decreasing. And ideally, we want to have a pattern that is evenly spread out, so it looks randomly dispersed along the x-axis for us to say that the assumption is satisfied. So here are illustrations of those cases. So here in this residual plot, we can see that the residuals are fanning out. So as this value changes, or as the value increases, we can see that the variation for the residuals are also increasing, and that is implied by the fanning out pattern. Now, if the residuals are funneling in, it means that as the value on the x-axis increases, the variation for the residuals are decreasing. And again, the constant variance assumption is satisfied if the residual plot relatively looks like this. So the residuals look like a horizontal band. The residuals are randomly dispersed, and they are not pronouncedly fluctuating as similar to the first two that we have seen. So as long as the residual plot looks horizontal and it looks randomly dispersed, then we can say that the constant variance assumption is satisfied. Now, another assumption is about the correct functional form. So the regression model used should be appropriate for the data. So you can see this, you can verify this in the scatter plot between x and y. So if there is a straight line or a linear relationship between x and y, then we can use the simple linear regression analysis. However, if the scatter plot shows a curved relationship, then instead of simple linear regression, then it's better to use a quadratic regression. So if the relationship between x and y is not linear, aside from the scatter plot, we can also see that in the residual plot. So the residual plot will also show us if the assumption for the correct functional form is violated. Now, for the normality assumption, we can check the histogram or the stem and leaf display of the residuals. And if the residuals look bell-shaped and symmetric, then we can say that the normality assumption is satisfied. Now, another way to check if the normal plot, if the
normality assumption is satisfied is through the normal plot of the residuals. So here it orders the residuals from smallest to largest, and if the normality assumption holds, the normal probability plot should have a straight line appearance. So this can be produced using different statistical software. So once the normal probability plot is produced, we just have to check if the graph looks like a straight line. If it's approximately a straight line, then we can say that the normality assumption is satisfied. Finally, for the independence assumption, again, the independence assumption says that the residual for a particular value of y and x should be independent from other residuals. Now, this independent assumption is normally satisfied, and this is only possibly violated when you have time series data. So if the data is not time series, then it can be reordered without affecting it. So in most cases, the independence assumption will be satisfied. But for time series data, the time-ordered error terms can be autocorrelated. So this is another concept which is exclusive for time series data only. So for positive autocorrelation, this refers to a positive error term that tends to be followed by another positive value, and negative autocorrelation happens when a positive error term tends to be followed by a negative value. So this can be seen by a cyclical error term over time. So you can see that the residuals follow a certain pattern. So here is an example of a plot that shows positive autocorrelation, while this one shows negative autocorrelation. So if these two can be observed, then we can say that the independence assumption is violated, and we can rely on the linear regression analysis in order to make statistical inferences. A useful test that can help us determine the presence of autocorrelation in the dataset or in the residuals is through the Durbin-Watson test. So in the Durbin-Watson test, we compute for this value small letter d, and this will be the basis of our interpretation for the presence of positive or negative autocorrelation in the residuals. So this is the formula for D, and this is automatically computed using different statistical software. In the Durbin-Watson test, there are two kinds of tests that we can perform. First is a test for positive autocorrelation, and the second one is a test for negative autocorrelation. For the first test, where we test if the residuals are positively autocorrelated, these are the hypotheses. So the null hypothesis states that the residuals are not autocorrelated, and the alternative hypothesis states that the residuals are positively autocorrelated. Now, to perform this test, we need the value of D, which is computed using the formula shown earlier, and then we will compare this to two values so that we can make an interpretation. The values are D sub L alpha and D sub U alpha, and these are values or critical values that we can obtain from the Durbin-Watson table. It's in the appendix of the Business Statistics Practice textbook. These values can be determined based on two values. We need k, the number of independent variables, and we also need n, the number of observations in the dataset. Furthermore, you also need the value of alpha to determine the value for the DL alpha and DU alpha, which should be compared to the test statistic D. Now, if the D is less than the lower value, that's DL alpha, then we reject the null hypothesis, which means that the residuals are positively autocorrelated. But if D is greater than the upper critical value, then we do not reject the null hypothesis, or the residuals are not autocorrelated. However, if D is in between those two critical values, then the test is inconclusive, meaning we cannot say if the residuals are autocorrelated or not autocorrelated. Now for the second test, we test the residuals for negative autocorrelation. And here, instead of comparing D to the lower and the upper limits, we will compare 4 minus D. So it's almost similar to the first one. If 4 minus D is lower than the lower limit, then we reject the null hypothesis, or we can say that the residuals are negatively autocorrelated. But if 4 minus D is greater than the upper limit, then we do not reject the null hypothesis, which means that the residuals are not negatively autocorrelated. Finally, if 4 minus D is in between the two critical values, then again the test is inconclusive, meaning we cannot tell if the residuals are negatively autocorrelated or not. The third test is a combination of the two. So we can perform a test for positive and negative autocorrelation at the same time by looking at D and 4 minus D. In fact, we have to perform both tests in order to perform this specific test. Here, we perform both tests for positive and negative autocorrelation, and then the interpretation will depend on the results of those two tests. First, if either test says to reject the null hypothesis, then that should be the correct interpretation. For example, if we perform the first test and we were able to conclude that there is positive autocorrelation, and then the second test says that there is no negative autocorrelation, then we can say that there is positive autocorrelation. So either test should be able to reject for us to say that that is the kind of autocorrelation present in the residuals. Next, if both tests say that we should not reject the null hypothesis, meaning there is no positive autocorrelation and there is no negative autocorrelation, then it means that we do not reject the null hypothesis as well, meaning the residuals are neither positively nor negatively autocorrelated. Finally, if either test is inconclusive, meaning any of these two tests results to inconclusive results or interpretations, then it means that the overall test is inconclusive. So if the first one is inconclusive and the other one is do not reject the null hypothesis, then it means that we cannot say if the residuals are autocorrelated or not. Now I'll show you an example on how to perform simple linear regression in Microsoft Excel. So this Microsoft Excel version is the Microsoft Excel for Mac. This is the latest version, and the latest version allows me to use data analysis in Microsoft Excel itself instead of using other statistical software. So here I already have data analysis because it's present in this version of Microsoft Office. And this dataset is still the same Rustan's Katipunan dataset, and this is the clean worksheet. Now, to perform simple linear regression, I'll pick two quantitative variables. So for this case, I'm interested to test total amount spent against number of people in the household. So to perform the test, I have to copy this to another worksheet first, and then I'll also copy the other variable, number of people in the household. And now that I have these two variables isolated, I can now perform the test by clicking data analysis, and then I'll choose regression, and then make certain selections. So for y, or the dependent variable, my selection should be the total amount spent. So this is my dependent variable. And then for x, it should be the values here under household. Since my selection includes the first row, the column labels. I'll make sure that this is also checked, labels part. Now for output, you can choose to put the output in the same worksheet, like this one in D1, or you can have the output of the simple linear regression test in another worksheet. And to verify the assumptions of simple linear regression, I check residual plots and normal probability plots. Now, once you're done with this dialog box, just click OK, and now the output will appear. Now, before we make any interpretations, again, we have to look at the graphs. And here are the graphs that were constructed using simple linear regression. So I'll resize these graphs in order to make better conclusions or interpretations using them. So here for the residual plot, we can see that the residual plot is relatively homoscedastic, so the variance is relatively constant across different values of x, and it looks more or less horizontal, so the constant variance assumption is satisfied. And now if you look at the normal probability plot, again, the goal here is to see if the normal probability plot more or less follows a straight line. And if it follows a straight line, we can say that the normal assumption, normality assumption, is satisfied. Now, if you look closely at this normal probability plot, it shows us a more curved normal probability plot. It doesn't really look like a straight line. So it's very far from a straight line actually, which means that the normality assumption is violated. And in this case, it's no longer proper to interpret these values because the assumption on normality for simple linear regression is not satisfied. Now, I'll test another pair of variables in order to perform and demonstrate simple linear regression. So instead of looking at total amount spent, I'll now consider number of items bought as my dependent variable. So I'll copy that and paste that in another worksheet. And then now I'll use the same independent variable, which is the number of people in the household. So now that I have the data prepared, I can perform simple linear regression. So my y should be the number of items bought. Number of people in the household is my x. Labels is checked. Output range is also this area, D1. And I also have the residual and normal probability plots. So now I have here the results of the test. And if we look at the graphs, here the residual plot looks relatively horizontal again. So there are a few values that are very far, but we can consider these as outliers. So more or less, the constant variance assumption is still satisfied. Now for the normal probability plot, if we now look at the normal probability plot, it now looks more acceptable except for a few outliers. So these ones we can just ignore, and the rest are relatively close to a straight line. So now it's more acceptable, and we can now assume that the residuals are normal. So the normality assumption is satisfied. So now that we've checked these two, now we can try to perform the, or we can now try to interpret the results of the simple linear regression. So here we can see the ANOVA table. We have the F statistic and the p-value, and that's 0.2278. According to the F-test, this is an overall test for the model, and since the p-value is relatively high, then we can say that we don't have sufficient evidence to support the claim that there is a relationship or between the two variables, number of people in household and the number of items bought. Or in other words, we don't have enough evidence to say that the two variables are correlated. We can also look at the regression coefficients. We have here the y-intercept, and this is the slope for household. We can see that the y-intercept is significant. The p-value is very low, but the p-value for household is similar to the f-test. They have the same value and they're both higher than 10%, which means that this slope, this coefficient is not statistically significant, which means that again, we can say that there's not sufficient evidence to say or to support the claim that there's a relationship between the number of people in the household and the amount spent and total number of items bought. Now, the regression statistics also support that conclusion. We found earlier that there is no relationship between x and y, and that shows us low values for r and r square. So r square is just 1.42%. Multiple r is 0.1193. Again, these are very low values because, as shown earlier, the slopes are not statistically significant, which naturally produces low values for these. So these values again verify our conclusion that there seems to be no strong linear relationship between number of people in the household and the number of items bought. In this example, I have a different data set with three variables. I have month, sales, and advertising expenditures. Now, I am interested to test the relationship between the variable sales and advertising expenditures. And for me to do that, I'll use a different plugin, which is the Megastat plugin in Microsoft Excel. Here, I'll click on Megastat, and then I'll click correlation/regression, and then I'll choose regression, and then here a dialog box will appear, and I'll have to make selection so that I can perform the correct test. Here, the independent variable will be the advertising expenditures, and then my dependent variable will be the sales. So I'm interested to see, aside from knowing if there is a relationship, I'd like to know if advertising expenditures are good in predicting the sales for a particular month. So I made these selections for these two columns, and then here I am choosing no predictions because I'm not predicting for another particular value for advertising expenditure. Now, in order to validate the assumptions, I'll be checking the following. So here I have a check for output residuals, and then to check for independence or the presence of autocorrelation, I'll click Durbin-Watson. Now, I'll also be checking this one, plot residuals by observation instead of plot residuals by predicted y and x. Because for this case, although the data set, the two variables are not really time series, this is still time series because the data is ordered by time. So the rows are ordered by time, by the month. That's why it's still appropriate to use a residual plot based on time, not a residual plot for predicted y versus the value of x. And then finally, to validate the normality assumption, I'll also have to check the normal probability plot of residuals. Now, if you click OK, the plugin will show you another worksheet with the following values. So here it shows me the regression results. Here I have the r squared, the r, the standard error. It shows me the number of observations, 24, and the number of independent variables, which is 1. And here I've selected sales as the dependent variable. Now, similar to simple linear regression using Excel, we have the following values. So again, I have here the y-intercept and values involving the slope, which is the slope for the independent variable for advertising expenditures. So again, Megastat also doesn't show the regression equation. It doesn't automatically show us the regression line, but we can easily construct that using the coefficients here in the table. So this is the value of the slope, that's negative 0.4487, and this is the value of the y-intercept, and that's 320.1086. So if we were to construct a regression equation, that's y hat, or the predicted value for y, or the predicted sales for a particular month, is equal to 320.1086, it's just a constant, minus 0.4487 times X, or X here again refers to advertising expenditures. So that is the regression equation based on this data set. Now, before we interpret the significance of these coefficients, we have to look first at the different plots in order to make an interpretation about the assumptions of simple linear regression. Here we have the normal probability plot, and as you can see here, it seems relatively straight. Therefore, we can say that the normality assumption is satisfied. But now, if you look at the residuals, again, as mentioned before, the residuals should look more horizontal. There should be a random dispersion of the residuals, and that's not something that we can observe here. As you can see here, it looks cyclical, it increases, then decreases, and so on. And again, this is indicative of autocorrelation, and that can be verified by the Durbin-Watson statistic. In this case, it's 0.47, and in order to test for positive or negative autocorrelation, we have to compare this to a lower and an upper limit using the Durbin-Watson table. Now, using the table for k equal to 1 and n of 24, the lower limit should be 1.04 and the upper limit is 1.2. So this is the value of D, and this is definitely lower than 1.04, which means that there is positive autocorrelation. So it's again consistent with the residual plot that we have here. This doesn't look horizontal, and according to the Durbin-Watson test, there is positive autocorrelation. Now, you can also test for negative autocorrelation. So in order to do that, you'll have to compute first for 4 minus D, and that's 3.53. And in this case, this is greater than the same upper limit of 1.2, which means that there is no negative autocorrelation. So combining those two, there is positive autocorrelation and there is no negative autocorrelation. So ultimately, the conclusion is that there is positive autocorrelation in the dataset. So again, even if the dataset itself, the two variables does not include time, this is still considered time series because the data is arranged by time. So the rows are arranged by time. That's why this is still considered as time series data. And we have to verify the residual plot by time. And we also have to interpret the Durbin-Watson statistic. So as we can see here, some of the assumptions of the simple linear regression are violated. Therefore, we cannot make interpretations on the other computations of simple linear regression. So we don't have to interpret the p-values of each coefficient. We also don't need to interpret the p-value of the ANOVA. And there's also no need for us to interpret these values because, again, the assumptions of the simple linear regression are violated.